Yeah, thanks.
Okay, great. We see your screen, we see your cursor, we hear you.
Perfect. That is all I need. Yeah, thank you very much for giving me the opportunity to speak. And the work I'll be presenting today on carbon-enhanced metal poor stars in the inner galaxy has been done in collaboration with a lot of people from the PRISTINE collaboration. And here I specifically want to thank again our Australian observers, many of whom are in the audience, who helped us a lot with the PIGS observation. So thanks again. So the very metal poor stars are interesting for various reasons. And when I say very metal poor, I care about stars below melicities of -2 in general. So in the galactic halo, there are many carbon-enhanced metal poor stars, which means that they have a large carbon overabundance according to this relatively arbitrary definition. So here is a compilation of very metal poor halo stars, the metallicity versus the carbon abundance. So you have a blob of carbon normal stars down here, and these very, very carbon-rich objects above this definition line. And there are two types of carbon-enhanced objects. There are the CMP-S stars, which form a very clear blob here, and the CMP-No stars. And they form in different ways. So the CMP-S stars are typically thought to form through binary interaction. So most of them are found to be in binary systems. And on top of their carbon enhancement, they also show an enhancement in S-process elements like barium. But then the CMP-No stars are the stars that go to the very lowest metallicities. And these are thought to be connected to the first stars and processes in the first stars. For example, faint supernovae, where you only have the outer regions with the lighter elements being expelled and the heavy elements are locked up, or rapidly rotating spinning stars that can create overabundances of carbon. So CEMP stars are interesting because they tell us something about binary stars, binary interaction, binary fraction. And CMP-No stars are interesting because they tell us something about the very early universe. So if we think about the metal poor Milky Way, we usually think about the halo, and we study the halo locally because we are here, and we typically look out of the galactic disk, especially if we're looking for the very, very metal poor stars, because they're really rare and you have the largest chance to find them in these less dense and metal poor areas. But that means we're completely avoiding the very inner regions of the galactic halo and the bulge. And this is interesting to study the most metal poor stars there as well, because they might be born in slightly different environments and they might have different properties. But finding the stars in the bulge is really tricky, especially if we go to the very metal poor stars, because they are outnumbered by very metal rich stars. And of course, there's also the dust that we have to get through. So this is where the PRISTINE survey comes in. The PRISTINE survey is a photometric survey using a narrow band filter centered on the calcium H and K lines. So this filter is on the CFHT, and this calcium HK photometry is really sensitive to the metallicity, even at very low metallicities. We can see here 3 spectra, -2, -3, -4. So if you combine this metallicity sensitive filter with broadband photometry to get an idea of the temperature, you can make a color diagram. So here we just have a normal color, and then on the y-axis we have calcium HK in a combination of broadband photometry. So here we see that if we have the spectroscopic information, that the metal poor stars still separate very nicely from the metal-rich stars. So for stars for which we don't have spectroscopy yet, if they're in this part of the diagram, they're likely to be really metal poor. So we can pre-select them very efficiently and exclude all the more metal-rich stars. So the PRISTINE survey is mainly focused on the galactic halo, which are all of these patches that are still being filled up. But then there's also the inner galaxy, and this is the PRISTINE inner galaxy survey, or PIGS, where we're focusing on the very central regions and trying to find the metal poor stars there. And we've done some spectroscopic follow-up of the interesting metal poor candidates using the AAT with A omega and 2DF. So the footprint we have here is limited because we are, the photometry is limited to the northern hemisphere, the northern part of the bulge. And we're avoiding the really, really extincted regions. So we have about 12,000 spectra with low resolution optical spectra and a bit higher resolution calcium triplet spectra. And we use these to get the radial velocities and the stellar parameters with the ferrocode. And we can get the three main stellar parameters and the carbon abundance. So what do we find? How metal poor are the stars in our 12,000 star sample? So here's just a comparison with more standard bulge surveys that don't select for metal poor stars. And we can see on average, they're really metal rich. They have practically no stars below -2. So the first large dedicated metal poor bulge survey was the EMBLA SkyMapper survey. They were very successful at targeting the metal poor tail, and for the first time having a very large number of the most metal poor stars. So they use a similar technique as Pristine. We actually were inspired by their technique. And then with the even narrower filter and the addition of Gaia and better extinction maps, we've been able to get an even better success rate at finding metal poor stars. And we have the largest sample of very metal poor stars, about almost 2,000 stars in the inner galaxy region. So for almost all of these stars, we also have their carbon abundances. So it's interesting to see how do the carbon enhanced properties compare to stars in other regions of the halo. So before PIGS, there were only a handful of stars in the bulge known. So these are the star symbols compared to a halo compilation of carbon-rich objects. So here I'm only showing the carbon-rich objects. So only 6, 7 carbon-rich objects were known in the inner galaxy. And with PIGS, we've actually been able to find 96 additional ones. So this is a huge increase of the number of carbon-rich objects that we can start to study and see what are their population properties. So it's interesting that we have all of these new stars, but what about the relative fraction, how often these occur? So in the halo, so actually PIGS has a lower fraction. In the halo, we have here the green line is the overall carbon enhanced fraction, which goes from about 35% to over 60%, and almost all of the stars at the lowest metallicities. And here it's just separated by the different subcategories of CE and P star. And if I then overplot the PIGS frequency, we can see that it is much lower than the overall fraction. And then at the lowest metallicities, it actually starts to agree better and better. So the discrepancy is highest for the higher metallicity stars. Okay, so we don't have the, okay, thanks. So we don't have the ability to separate between CMP-S and CMP-No because we don't have the S process abundances. But you can kind of separate them by making a division in carbon. And that looks like below -2 is roughly half of the different types of stars. So that means that there seems to be a discrepancy in both the CMP-S and both the CMP-No stars. So why do we see this low fraction in PIGS? There can be multiple things playing together. So first of all, there could be photometric selection effects playing a role. We're using the photometry to select very metal poor objects. But if you have a carbon-rich objects, and here I'm showing one of the first CE and P stars known, there's these huge carbon features in the spectrum that can mess up your colors. So we've investigated this, and this is unlikely the full explanation. Only the coolest, most carbon-rich, most metal-rich objects would not fall into our selection, probably. So what if there is a difference in CMP-No stars? And this is related to the properties of the first stars and or the early chemical evolution. So it can be that there's been faster chemical evolution in the building blocks building the inner galaxy, wiping out the signal of the first stars at higher metallicity. So you would only see it at the lowest metallicities, and then if you go to higher and higher metallicity, the medium is mixed and you don't see this rare signature of the carbon. And this could be similar to a possible difference in C and P stars in the dwarf spheroidals and the ultra faint dwarf galaxies. Alternatively, there could be a difference in the binary properties of the population if there's a lower fraction of C and P S stars. So it could be that there is a lower binary fraction overall, having fewer stars that interact. And maybe a suggestion that we make is it could be that it is related to a larger contribution of globular cluster stars in the inner galaxy, which has been seen recently. And globular clusters seem to have a lower number of binary stars and of carbon-rich or barium-rich objects. So to summarize, C and P stars are interesting in various parts of the halo to tell us about binarity and about first stars and early chemical evolution. With PIGS, we finally have a very large sample of the lowest metallicity stars, and we can start investigating these carbon-rich objects. And we found a low frequency of these stars, and this could point to some differences in the inner galaxy versus the rest of the halo. And then there's more to come on this in the near future, which will hopefully clarify some of the still open questions. So for example, with higher resolution follow-up or combining with Gaia proper motions to see what are the dynamical properties of these stars. And then in the more distant future, having a larger sample of these stars and very metal poor stars with chemistry with Foremost will be something to look forward to. So thanks.
Thank you very much, Anke. This looks great. Questions for Anke? Yes, Gary.
Great stuff, Anke. Interesting, really interesting. Have you got plans to follow up these stars with, say, higher resolution or medium resolution in the blue so you can see whether they actually have S-process characteristics from, say, the barium lines or the strontium lines?
Yeah, I would like to do that. Yes. So I'm hoping that someone will give us time to do that.
Well, we've got a 2.3 meter telescope. They're pretty faint, these objects, though, right?
Yeah. So most of the carbon-rich objects are actually on the fainter side. So they're in Gaia G down to 16.5. So 15.5, 16.5.
Great. Other questions? Yeah, Karen.
Hi, Anke, nice talk. I was wondering if you have ruled out systematic differences between, I know that the pristine, that the candidates have followed up with different instruments, and have you ruled out that systematic analysis effect could cause this 0.3 Dex offset in chem fraction?
So you mean a difference in the carbon abundance scale?
Yeah, that's right. Or the metallicity scale.
Yeah, so it's actually something we're investigating. But if the average carbon abundance of the carbon normal stars and things are very similar to the high resolution sample, so the average carbon abundance seems to be similar. So we don't have any high risk stars to compare directly to, but the average trend seems to be the same. And there's really just a lack of the very carbon rich objects.
Yeah.